Today we're not going to do that much different mathematically, but we're going to interpret our results a little bit differently. So let's recall the fundamental theorem of calculus part 2 says that the way to evaluate a definite integral is to find an antiderivative of the integrand and then to plug in the two limits of integration and subtract. If we change the integrand from just a function f to specifically a derivative of some function, we get this result here. So the antiderivative or an antiderivative of f primed would be called f, and plugging in the two limits of integration give us f of b minus f of a. This is seen as the change in the function f. You can recall that's part of the slope formula if you're finding the slope between 2 points, a f of a and b f of b. So this is the change in f on a to b. And so we can interpret now the integral of a rate of change, which is what I have here, the integral of f primed being the rate of f, is equal to the function's change on the interval a to b. So if I have a curve that's a derivative, as I do in this picture here, this area from 1 to 4 actually has some meaning. Okay, this is the change in f, how much f changes between 1 and 4. So once again, even if I don't have the graph of f in front of me or the function f in front of me, I can determine things like how much it changes by calculating these areas via integrals. So let's take a look at some examples here. Water leaks from a tank at a rate of 2 plus 5t liters per hour. So this function here is a derivative. If we want, we could give it a name. Since we're talking about water, let's call it w primed of t, so we understand it's a derivative, it's a rate, and w kind of stands for water here. So we'll let w primed of t equal 2 plus 5t, so we can talk about it in context now. T is the number of hours after 7 a.m. Okay, how much water is lost between 9 and 7 a.m.? So I want to go from a rate, this w prime of t is measured in liters per hour, to an amount. Okay, and the way we do that is to use the fundamental theorem, but to interpret it in a new way. So 9 and 7 a.m. would correspond to 2 hours after 7 a.m. and 4 hours after 7 a.m. And I'm going to notice that if I put w primed of t as the integrand, it's symbolically, this comes out to be w of 4 minus w of 2, which is the change in the amount of water w between 2 and 4 hours after 7 a.m. So to answer this question, we need to do the integral from 2 to 4 of 2 plus 5t dt. Simple enough calculation. We've done this several times already, but now our answer may have some more meaning in the real world. So let's see here. All right. An antiderivative that we can use is 2t plus 5 halves t squared, and we need to input the limits of integration, upper limit first, lower limit second. So that gives us 8 plus, let's see here, this would be 16 over 2, that's 8 times 5, which is 40. And now we'll subtract what we get when we plug in 2 into the antiderivative. 4 plus, this is 2 squared, 4 over 2 is 2, plus 10. So I get 48 minus 14, 34, and my answer is going to be liters. Now, in these problems, sometimes it's confusing what the units of measure are. And so we can give you a hint as to where to look by looking at the integrand. Okay, what is w prime of t measured in? The problem tells you that w prime of t is measured in liters per hour. Okay, and then this is dt, which remember is a change in time. And time here is measured in hours. So we can say that that's hours over 1, and the hours units will cancel. And so your answer is going to be in liters, which makes sense in this context. If you just take the statement that we just had, which is integral a to b f prime of x dx equals f of b minus f of a, and we put f of a on the other side, in other words, we add f of a to both sides, we get this little expression right here, which is going to be very important as we move forward. It says that my function value at time a added to the integral, which remember represents the change in the function f from a to b, will give me my value at b. That makes sense. I took where I started plus the change, and that's where I am now, f of b. And we're going to use this little formula, or this relationship, I should say, quite a bit. So here's an example. If f of 1 is 12, f prime is continuous, and the integral from 1 to 4 of f prime is 17, what's the value of f of 4? So let's do some symbols. We know that the fundamental theorem tells us that the integral from 1 to 4 of f prime of x dx is symbolically equal to f of 4 minus f of 1. Our goal is to solve for f of 4. So if I add f of 1 to both sides, I'll have f of 4 isolated. And if you look up, this is the same formula that's written up there, just with 1 plugged in for A and 4 plugged in for B. So we can evaluate now the value of f of 4 if we know the value of the integral and the value of the starting value at f of 1. F of 1 was 12, the value of the integral is 17, and so f of 4 is going to be 29. You're going to get quite a few problems as time goes on. The AP loves these type of problems where they give you the derivative, they give you one function value, and they ask you to find another function value, which involves this formula, which involves finding an integral, which there are many ways to do now. You can think of it as a formula and do the antiderivative. You can think of it as an area and do it geometrically. In this case, they gave you the answer, which is not always going to happen. All right, and sometimes you have to use technology. So we'll talk about that in a second. There's a necessary calculator piece here. But here we go. We're given the derivative of a function f. We're given a one function value. We want to find another function value. So let's set this up. We know that if I'm going to go from f prime to f, I need an integral. So let's do this symbolically first. We're going to do the integral of f prime of x dx. Specifically, we want to go from where? The two values that I'm asked about. Okay, negative 3 is going to be 1, and 1 is going to be the second. In symbols, this is equal to f of 1 minus f of negative 3. All right, my goal is to solve for f of negative 3. So I'm going to add that to both sides, and then I'm going to subtract the integral from both sides so that I have f of negative 3 as a positive quantity isolated on the right side. So f of negative 3 is going to be equal to f of 1, which again is given to me, minus this integral from negative 3 to 1 of f prime of x dx. Okay? Now, if we can, we'll do the integral by hand. Or if I'm given a graph, I can think of it as an area and use geometry to find the value of the integral. In this case here, I have an integral that has an integrand that I don't know an antiderivative for. Okay? We don't know an antiderivative for sine of x squared. I know sine of x is antiderivative, or one of them, but I don't know sine of x squared. It's a problem. And so in this case, we need to use a calculator to help us evaluate that integral. And the calculator does it by doing a Riemann sum very quickly. So we are appreciative of that fact. We know we could do it slowly by hand or with Riemann sums, but the calculator will do a quick Riemann sum that will give us an approximation for this integral. So let's take a look. So we're going to do 1.2345 minus an integral. And an integral is going to be found in the calculus menu. And we're going to say from negative 1 to 3 of sine of x squared, and then we want this to be dx. And we do control equals, and that gives us a approximate value for that expression. So there we go. Our value for f of negative 3 is going to be 0.150 or 0.151, accurate to 3 decimal places. Okay, finally let's take a look at this from a graphical point of view. Here is the graph of f prime of x. We are told that f of 1 equals 0. So f of 1 is a known function value, and after that we don't know anything except that this is the graph of f of x. So let me go ahead and draw in a line here that kind of just tells us that this is where things begin to our function f, because I have a function value that we have a starting place for, and because we know what the behavior of f is going to be like, based on the behavior of the derivative, we can make lots of conclusions. For example, before we get into any calculations, because f prime is positive from 1 to 4, I know that f is going to increase from 1 to 4. And so that means we're going to go from f of 1 equals 0 to values larger than 0. Then we'll have a decrease from 4 to 6 because f prime is negative on that interval. And then from 6 to 7, f will increase again. The difference between this problem now and where we were before is we can actually calculate function values. Now let's talk about how we're going to do that. Okay, it'd be nice to have a formula for f of x, and we can get one. Again, we have a derivative and we have two function values. One is a general function value, and one is f of 1. So we can connect those three symbols with the fundamental theorem. So we could say the integral from 1 to x. Now I can't use f prime of x in here. I have to change the variable. And it can be anything I like. Generally speaking, we use the variable t. as a dummy. But what is this equal to symbolically? Well, it would be equal to f of x minus f of 1 by the fundamental theorem part 2. If I want to solve for f of x, I can add f of 1 to both sides, and now I have a little expression that will allow me to find some function values, as long as I can calculate values of this integral. And geometrically, I can do that. This function f will increase from 1 to 4. Okay, we're at 1, 0 on the graph of f, and we'll increase until we get to 4. And that's going to be a local maximum, right? Because f prime changes from positive to negative. So we might want to know, okay, what is f of 4? Okay, and now we have a way to do that. So f of 4 is equal to the value of the function at 1 plus the change that occurs between 1 and 4, which is interpreted here as the integral from 1 to 4 of f prime of t dt. And if I look at the graph, I can interpret that as the area under the curve f primed from 1 to 4. So if I can calculate this area, I'll know what to add to f of 1 to give me a function value at f of 4. It's really kind of neat. Okay, so we're taking old concepts now and just adding this new idea about the fundamental theorem to give us more information. So I can calculate this area. It's a couple triangles and some squares, or it's a couple trapezoids, however I want to think of it. But I count 4 squares here, and then this is going to be half of 2 squares, so that's 5. And if I put these 2 triangles together, I'll have 2 more squares, so that's 7. So f of 4 is going to be 0 plus 7. And we could do this for a whole bunch more function values if we liked, and we could do a pretty good analysis of f and draw a graph of f just by doing these same calculations. But it starts with writing the function for f of x using the fundamental theorem.